Okay, so last time we talked about what you can see in the sky with your naked eye, and we'll keep going down that path, and we'll learn about how the moon changes, how it looks in the night sky, and things related to the moon, the earth, and the sun. So we'll talk about looking at the moon and eclipses. So to review what we talked about last time, our modern way of keeping time all deals with astronomy. So years, months, week, days, hours, they all have roots in ancient astronomy. And then we finished the class by talking about how it's actually the tilt of the Earth's axis of rotation that causes seasons. It's not different distances between the Earth and the Sun. So let's see how well we remember. So which of the following of these choices are due only to the motion of the Earth? And there's multiple correct answers. Okay, so the length of the day is the Earth rotating on its axis. The length of the year is the Earth orbiting the Sun. Stars appear to rise and set because the Earth is rotating on its axis, and the length of the hour is taking how long it takes for the Earth to rotate on its axis and dividing it by 24 because ancient Egyptians used a base 12 number system. We'll talk about the length of the month during this lecture, and that's going to be actually due to the motion of the moon. And then on next lecture, we'll talk about where the length of the week comes from. But those two are not due to the motion of the Earth. They're due to the motion of other things. Okay, so there's one more motion of the Earth that we need to cover. So the Earth rotates on its axis and it orbits around the Sun. But it turns out that if we draw a straight line through the pole, through the North and South Pole, where that points in space is actually not consistent. So the axis of Earth's rotation actually wobbles a little bit over time. So this is called precession. And so here's an example of what that looks like. So the yellow dots are tracking where the line between the North and the South Pole is pointing. And so you can see over time, it's pointing at different constellations on the sky. And so you can think about this kind of like if you spin a top, the top of the top will start to wobble as it slows down. The Earth spinning on its axis isn't really slowing down, but it is wobbling as it spins. And so the spin is on a 20-something thousand year cycle. So the Earth rotates about its axis, causing days. It orbits around the Sun, causing years. And the axis of rotation kind of wobbles over time, and that's responsible for, when we talked about horoscope signs last class, I said that the horoscopes don't quite point where you would expect them to point anymore, and this is why. It's because the axis of rotation has wobbled a little bit, and so it's no longer pointing exactly at the horoscope sign that you would expect it to. But over this 20,000 year cycle, it will eventually point back to where it was originally pointing. And so here's just another graphic of that 26,000 year period. And so another consequence of this is Polaris will not always be the North Star, or it will not always be exactly above the North Pole, basically. So currently, it is just about at the north, above the North Pole, but over time, so here's where Earth is pointing today, and in 15,000 years, the North Pole will be somewhere near the Vega constellation, rather than being part of the Little Dipper, or where a North Star might be. And so things like the equinoxes will change. So currently what constellation is in the sky for the spring equinox is Aries, but eventually it'll shift over to Pisces. So the time of year that you might associate a constellation with is going to change, and that's why your star signs don't necessarily match up. Okay, so the tilt of the Earth's orbit is what causes the seasons, and that tilt, so the Earth is always tilted by that 23.5 degrees, but where the North Pole is pointing on the sky changes with this 26,000 year precession cycle. And so these are the three ways that the Earth is moving by itself. So it's spinning on its axis, it's orbiting the sun, and its axis of rotation is precessing. That's not taking into account all the ways that the sun is moving around the galaxy, for example, and the galaxy is moving with respect to other galaxies, which of course means the Earth is moving with all those motions as well. But just by itself, the Earth is doing these three types of motion. So then we'll move on to talking about the moon. So this is the thing that orbits the Earth, and we'll talk about the phases of the moon, and then we'll talk about how the moon causes eclipses. Okay, so why do we see phases of the moon? So the moon goes through phases, going from a full moon to half moon, and then new moon, and then back again, and that cycle takes about 27 days. It takes the moon 27 days to go around the Earth. We'll talk about how long it takes for the lunar phase to actually go through a complete cycle. And so that happens because the moon is orbiting around the Earth, but the moon does not generate its own light. So the only light that we can get from the moon is sunlight bouncing off of the surface of the moon and then coming towards the Earth. So in this picture, the sun is down in the bottom left of this picture. This circle is the orbit of the moon. And so at different points on the moon's orbit, different sides of it are going to be illuminated. And I think, there's a better diagram here. So here the sun is in the top left of the picture. You're the person in the middle, you're standing on the Earth. And so if the moon is in between you and the sun, then the part that the sunlight is hitting is illuminated, but you can't see that illuminated side because you're back here. And so then as the moon goes around the Earth, and it takes that 27 days to orbit the Earth, Now, at this position, it's still half of the moon that's illuminated, but you're able to see part of the illuminated part of the moon. Then, I guess I went in the wrong direction, so we'll go this way first. So you're seeing a little bit of a sliver. At this position, it's still half of the moon that's illuminated. It's just that you can now see more of that moon that's illuminated. And as we keep going, eventually now, sun is still over here. Now the face of the moon that's totally illuminated is the side that's facing the Earth. So now you can see all of the illuminated part of the moon. And so we go through these different phases. So crescents are when you're less than a quarter. Waxing is when you're increasing the amount of bright side of the moon that you can see. Then you go to your first quarter. Waxing gibbous. So gibbous is when you're above the quarter threshold, or there's more of the moon illuminated than the quarter threshold. And waxing, we're still revealing more of the illuminated side of the moon. And then we get to full moon. And now we're waning. So waning is when we are decreasing the amount of the illuminated side of the moon that we can see. Waning gibbous, third quarter, waxing crescent, and then back to new moon. And the time that the moon rises and sets will also change with the phase of the moon. So a new moon rises and sets with the sun. A full moon will rise at sunset, be at the highest point at midnight, and then set at sunrise. And there will be different rising and setting times for each of the different phases in between. And here's another picture in case the person in the middle was kind of confusing. So here's the Earth and the moon orbiting it. The sun is on the right side of this diagram. And so in this picture you can always see it's always half of the moon that's being illuminated by the sun. It's just what part of the moon can you see from the Earth will determine what phase the moon is in, which is on the outside edge. So the phases of the moon actually are in a 29.5 day cycle. So that's how we get about a month being about 30 days. And so the waxing moon and the waxing moon being on the right and the waning moon being on the left is for the northern hemisphere. So these are the phases, and they always go in this order. So you're always going new, waxing crescent, first quarter, waxing gibbous, full, then waning gibbous, last quarter, waning crescent, and then back to new. And so if you see a crescent and it's in the right-hand side of the moon is illuminated, then you know that it's a waxing crescent. And if you see the left-hand side of the moon being illuminated for a crescent moon, then that's a waning crescent. So if you've been paying close attention, you'll notice that there's a mismatch here. I said it takes the moon 27 days to orbit the Earth, but the lunar cycle is 29 and a half days. So can anyone think of a reason why these numbers don't match up? Maybe you can come up with a theory with the people next to you. Yeah, so it does have to do with the position of the Earth, the Moon, and the Sun. So remember, the Earth is not just sitting still as the Moon is orbiting the Earth, right? The Earth is also orbiting the Sun. So if we look at this new moon, or if we look at this picture, so this is the new moon. It's going through its cycles, but the Earth hasn't just stayed in this spot. The Earth is orbiting the sun during this lunar cycle, and so the time it took for the moon to get back to the same place in its orbit, right? So it's in the same orientation it was with respect to the Earth, but we're not quite back to being in the way of the, we're not quite in the same line with the sun, right? We would need the moon to be over here to be in the same line. So that extra 2.5 days is because as the Earth has orbited the sun, it takes a little bit of extra time for the moon to get back into the orientation for it to be a new moon. So if the Earth wasn't going around the sun, then the time it takes the moon to orbit the Earth and the lunar cycle would be the same number. But because the Earth is also moving around the sun, the moon has to catch up for 2.5 days to get back to the new moon. So that's why there's this mismatch. So it's 9 a.m. and you look up in the sky and you see a moon that has the left side bright like this and the right side is dark. So what phase of the moon is that? Okay, so it's the left side, so it could be waxing, but the picture of the moon itself looks like it's just about at half illuminated and half not. So that tells us it's either the first quarter or the third quarter, and the fact that the left side is illuminated means that we're in the second half of the lunar cycle, which means we're in the third quarter. If it had been the right side that was illuminated, then it would have been first quarter. And then there's no such thing as half moon in the lunar cycle. So just by looking at the moon, you should be able to tell which cycle you're in, or which part of the lunar cycle you're in. Okay, so the moon orbits the Earth, and just like the Earth spins on its axis, the moon also rotates on its axis. That rotation is actually synced with its orbit, though. Side of the moon that we see is always the same side. So there's a far side of the moon, which is the side that never faces the Earth, but there's no such thing as the dark side of the moon, because we saw with the lunar phases, there's the half of the moon is always illuminated, and that changes as it goes around the Earth, or around the Earth. But the same side is always facing the Earth. And this is a type of orbit that we'll come back to when we talk about exoplanets, so planets orbiting other stars. This is a special type of orbit. The moon goes around the Earth is going around the sun, and sometimes those orbits all line up in such a way to give us an eclipse. So remember, the sun is the only thing that creates light in the solar system, and so when that light hits the moon or the Earth, whatever's behind that will be in the shadow of either the moon or the Earth. So in this diagram, here's the sun, here's the moon, and anything that's directly behind the moon such that you can't see any part of the sun is going to be in this shadow. And so if you are on the Earth and the Earth happens to be, or some place on the Earth happens to be in the shadow, then you have what's called a solar eclipse, where the sun is being eclipsed by the moon. And so here's a video of a total solar eclipse. So this shadow is the moon crossing in between the Earth and the sun. And depending where you are for a given solar eclipse, that total eclipse can last for on the order of a few minutes. So I will talk about a lunar eclipse or a solar eclipse that happened recently, and I saw the totality or the time when it was fully eclipsed for about 3.5 minutes. But if you're really lucky, it can go up to 6 minutes for a total eclipse. It's not just the moon that can cast a shadow, but the Earth can also cast a shadow onto the moon. So that's called a lunar eclipse. So we had a total lunar eclipse in March this year. We'll talk about the conditions for the eclipses in a little bit, but lunar eclipses are much more frequent than total solar eclipses. And so you can see the shadow of the Earth passing in front of or across the face of the moon. And the moon didn't really get brighter. It's just that the bright part of the moon is very bright compared to the dark part of the moon. So when there's no bright part of the moon in sight, it's easy to see the red color of the moon during a total lunar eclipse. But as soon as any part of the moon is not in the shadow, it becomes very bright. And then this particular lunar eclipse didn't quite end before daytime happened, so that's why it got bright at the end. So there's these two different types of eclipses. There's the lunar eclipse and the solar eclipse. Lunar eclipse is where the Earth is casting a shadow on the moon. And then a solar eclipse is when the moon is casting a shadow on the Earth. The phase of the moon is related to what type of eclipse can happen. A lunar eclipse can only happen during a full moon, and there can be penumbral, partial, or total lunar eclipses. So if the moon is completely in the Earth's shadow, then that'll be a total lunar eclipse. A partial lunar eclipse will be when part of the moon is in Earth's shadow and part of it isn't. And a penumbral lunar eclipse will be where so the penumbra is this kind of purple shade where a little bit of sunlight is being blocked, but not very much. So this penumbra is a partial shadow, whereas directly behind the moon or the Earth is a total shadow. And then total solar eclipses have, there can be total solar eclipses. There are other types of eclipses as well. Here's a time lapse of an eclipse in 2017 taken over Wyoming. And so these are the position of the sun on the sky over the course of the day. And you can see starting here, more and more of the sun is being covered. And then eventually you get, this one might not have been a total solar eclipse, this might have been an annular eclipse, because you can still see a bit of the sun. And then the moon starts moving away from the sun in the sky, and so the shadow of the moon is no longer over the Earth. So these are the diagrams for the solar eclipses. So solar eclipses can only happen at new moon. So lunar eclipses happen at full moon, solar eclipses happen at new moon. And solar eclipses can be partial, total, or annular. So this is a total solar eclipse where, and it's not, the whole Earth is never in a solar eclipse. We'll see some maps in a little bit that show the path that a total solar eclipse takes over the surface of the Earth, but it's never the whole surface of the Earth. It's just certain segments of the Earth that can see the total solar eclipse. If you're not in that path, what you'll see is a partial solar eclipse where on the day of the eclipse, the moon will cover part of the sun in the sky, but it will never cover the whole thing like in this picture. And then an annular eclipse is the same configuration as the total solar eclipse, but when the moon goes around the Earth, and we'll learn in the maybe next week that orbits are not perfectly circular, they are elliptical. So as the moon is going around the Earth, sometimes it's a little closer to the Earth and sometimes it's a little farther away from the Earth. When the moon is too far away from the Earth, its angular size in the sky will actually be smaller than the angular size of the sun. And so when the moon is just a little too far away from the Earth, you'll get an annular eclipse. Certain conditions that you have to meet in order to get a total solar eclipse. But why? So we said a solar eclipse can only happen at new moon, and the orientation is just sun, moon, Earth. So why don't we get a total solar eclipse every new moon? Maybe this will be another time where you can talk to the people next to you and try to come up with an idea for why we don't get a total solar eclipse at every new moon. And let's say total or annular, because we don't get these eclipses very often. So just like with the difference between the lunar cycle and the time it takes to orbit the Earth, there was some motion that we didn't know about or weren't considering. So there's a motion that we are not considering here, and it has to do with the plane that the moon orbits the Earth. So we'll talk about the formation of the moon in a few weeks and basically the plane that the moon orbits the Earth is not the same plane that the Earth orbits the sun. They're slightly offset from each other. And so they're offset by about 5 degrees. And so the result of that is that there are only a couple of times during the year where the moon is in the same plane as the Earth and the sun. So when the moon crosses the ecliptic, which is the plane that the Earth orbits the sun, that's called a node. And there's only 2 nodes every year. And so in order to get the total solar eclipse, you need the new moon position, but you also need new moon to correspond to the time when the moon is crossing the ecliptic. And so there's an extra dimension of space that you have to worry about. You don't just need things to line up where the moon is in between the sun and the Earth, but you also need the moon to be crossing the plane that the Earth goes around the sun. And so there's 3 conditions that you have to meet. So you have to be in a full moon, or this is for the lunar eclipse, you have to be a full moon, or for a solar eclipse, you have to be at new moon phase. So the phase of the moon matters. The moon is orbiting the Earth, but its orbit is slightly at an angle compared to the plane that the Earth orbits the sun. And so the moon has to be pretty close to one of the nodes where it crosses the ecliptic. And then because the moon's orbit is slightly eccentric, meaning that it's not exactly circular, it has to be when it's closest to the Earth rather than farthest away from the Earth. So this perigee and apogee are vocabulary words that we'll come back to when we start talking about ellipses rather than circles. So 3 conditions for a total solar eclipse. If you only meet the first 2 conditions, you would get an annular eclipse. If you don't meet the first condition, there won't be any eclipse. If you meet the first condition but not the second condition, there won't be any eclipse. And if you meet all 3 conditions, then you'll get your total solar or total lunar eclipse. Here is a map of the total solar eclipses that will be happening for the next, let's see, what does it go up to? 40? So the next 20 years. This blue line going through the US is the total solar eclipse that happened last year. And then the red line that crosses that is the total solar eclipse that happened in 2017. So we were actually in Illinois very close to both of the intersection of those 2 total solar eclipses. So hopefully, if you are from Illinois, hopefully you got a chance to see at least one of those. If you didn't, the next chance you'll have is this kind of purple one going through Wyoming. And that one is, I think, this one in 2026. Or you can plan a nice vacation to Brazil in 2045 or Australia in 2037. So you can read this map and pick a date if you really wanted to see a total solar eclipse, but you didn't get the chance. So those 3 conditions that we needed for a total solar eclipse are on what's called a Saros cycle. And that's about an 18-year, 11 and a third day cycle. So if you look at the dates that these eclipses happen, they're not all happening on the same date. And this 18-year cycle is how long it takes for you to get all 3 of those conditions to line up. Yep.
Why are some of the lines way thicker than the other ones?
Yeah, so the ones near the poles are really thick because of the projection of the map. And also the ones that are like this, why is the red one a little bit thinner than the blue one? So depending on the distance between the moon and the Earth, the angular size of the moon changes. So if the moon is at its closest distance to the Earth, then you'll get a bigger shadow cast on the surface of the Earth. So another way you can think about these tracks is this is the shadow of the moon moving across the face of the Earth. So a wider track means that the shadow is a little bit bigger. Yeah, so like I said, there was a total solar eclipse in Illinois recently. We were a little bit unlucky in Charleston. We were just outside of the path of the eclipse, so we didn't have a total eclipse here. But I took some students down to Robinson, Illinois, and there we had about 3.5 minutes of totality. And so this is a picture that someone took through a telescope of the total solar eclipse as we saw it from Robinson, Illinois. And you can see some solar flares and prominences coming off of the surface. And when we talk about the sun a bit later in the semester, we'll come back and explain why there's these bright things coming off the surface of the sun. Okay, so the moon, half of the moon is always being lit by the sun, and the phase of the moon is just how much of that lighted side of the moon you can see. And then the cause for the eclipses is the orientation of the sun, earth, and the moon, and you need very specific conditions in order for you to have total eclipses.